Hello, my name is Lawrence Killer, and this is my explanation of Q-learning with an application on the cart-pole problem. So the basics of Q-learning, we have to define the optimal policy of an agent in a specific environment, and we do that by maintaining a Q-table. And this Q-table has as rows all possible states, and as columns all possible actions. And we then update these Q-values based on experience. So if you take a look, for example, on this environment on the right, it has 9 different states, and let's say we have 2 different actions, go up and go right, then the Q table could look like this and would be initialized with 0, for example. To update the Q values based on experience, we use the Bellman equation. You can see it here. It basically consists of 2 parts. The first part, to the left of the plus sign, is the old Q value multiplied by 1 minus the learning rate. The learning rate just says how much we value our old value and how much we value the new value. And that's on the right side, the new value. And that is basically the current reward that we got for this state action combination. And then we add to that the maximum of the new reward in the new state. And this maximum gets also applied in the discount factor. With this discount factor, we can basically say how much we value future rewards in relation to current rewards. So, for example, if we take a look at the environment again and we introduce an agent and some kind of hazard, we could say our alpha would be 0.2, our gamma 0.8, and our agent is currently in state 6. And we don't know the next state, also not the action and the reward. So for example, we choose an action based on their Q values because they're both 0. We choose a random one, for example, upwards. When we go there, we update our values. We get a reward of 1 for going there. Action is 0, that's basically the index, and the new state is number 3. And now we need to update the corresponding Q value, so this one here. We just plug all these things into the formula, we get 0.2. Next up, we would have to update these parameters again, so now we're in state number 3, and these are unknown for now. So if we want to go, for example, to the right now, we set the action to 1, and if we go there, we see, oh, that was bad, there's a negative reward of -10. And now we just take all these again, plug it into the correct Q value in the table. So this one here in state number 3 for going to the right. And if we do that, we will get -8. So next time we're in this position, we will see, oh, maybe it's better to go up instead of go right into the fire. And then we need also to introduce some kind of randomness to explore the environment instead of always acting according to the Q table, and that is done with the epsilon value, which is between 0 and 1, and you can basically see it as a probability to choose a random action instead of exploiting the Q values. So again, an example, we are in this situation, we use the Q table from before. We're in state number 6, so we would normally use go to the right, to the up, because we have a higher Q value here than there. But if we introduce an epsilon, it could randomly happen that it says, oh, I don't want to take this action. Instead, let's take a random action. For example, the random action is going to the right. And then by going to the right, we get a reward of +10, update the corresponding value. And now we even know that going to the right in this state might be better than going up. So now let's take a look at the cart-pole problem. Well, this problem in the environment here consists of a cart. We have a pole on top and we need to keep it balanced as long as possible. The actions for every time step is just pushing the cart to the left or to the right. And the perception is the pole angle, the pole velocity, the cart position, and the cart velocity. The episode can end in 3 ways. So way number 1 is if the cart leaves the track. Number 2 is if the angle of the pendulum exceeds 15 degrees in any direction. This can actually happen quite fast, as we can see. Or the good ending is if our episode length reaches 500 steps. So to get the states, well, we have continuous values in our observation, so we need to cut them into discrete states. Here's an example of how that could work. For our agent, we will use only pole angle, as you can see here, and the pole velocity, and map them both to 21 substates. That means if we combine them into one state, we have 441 states, and with two possible actions, that means our Q table has 882 entries. Now, let's take a look at the parameters we use for the Bellman equation. We will say the reward is 1 if the poll is still standing, or minus 1000 if the episode ends in a bad way. To punish this, we also say the discount factor is 0.9 because we have a lot of states. It might be good that we value future rewards higher. We also say let's take a learning rate of 0.1. And we start with epsilon being 1, so just taking random actions, and then we decrease it by 0.0005 for every episode. And then we let our agent learn for 3000 episodes, so until episode 2000 we will have some kind of epsilon chance, and afterwards epsilon will be 0 and we can exploit the best strategy. And if we do this, we can plot the results, and you can see the points here are the scores for each episode, and I've also plotted the moving average. So we definitely learn, and you can see that we're actually doing an effort of balancing the pole. But in the end, when our epsilon reaches 0, here we can see that we try to exploit the best strategy, but after some time this means getting rid of all these minimum and maximum values and then ending up in a situation like this. If you want to improve this, we take a look at our parameters and say, for example, we want to value it higher if our agent stays alive longer. So we, instead of using 1, we use the current episode score. So the longer the episode goes, the higher the reward will be. And if we try that again, we can see that it's definitely better than before. We are learning, and once we hit the epsilon 0, we are definitely exploiting the best strategy and hit an average value of about 450, which is actually good enough for today to say that we can say that Q-learning indeed does work. Thank you for watching. The code of the video of the Q-learning is linked in the video description, and see you in the next video.